Okay, welcome back everyone. So in today's video we're going to actually be doing a third example of finding the supremum. Except there's a twist in this video, as we'll see and we'll prove, there actually is no supremum in this case. And there's also no infimum. So this is kind of like, this one's probably going to be the most involved, since we actually have to prove that no supremum exists in this case. And the nice thing about this is that in doing this, we're actually going to prove that, and we're going to talk about the axiom of completeness later on. We're going to prove it as well. But this will actually show that Q, so the rationals, is not complete. We'll talk more about that later when we talk about the axiom of completeness, or the least upper bound property. Okay, so, well, we're given the set. So we're going to start by showing that the supremum doesn't exist. And to do that, well, let's give kind of a structure of the proof that we're going to do. Okay, so first we're going to consider the case, well, let's take some m. And let's say, by way of contradiction, suppose m is the supremum of E3, or set E3. Okay, well, let's consider two cases. So first, we're going to consider m squared is greater than 2. And then second, we're going to consider m squared is less than 2, meaning m is actually in our set, which is possible. We saw that if there is a maximum of a set, then that is actually the supremum. Note that the maximum is in the set, as we talked about. Well, 3, kind of a 3, both of these imply that if we show that the supremum does not exist, so if we have a contradiction for both of these, then, well, the third one will follow from both of these, that the only case is that m squared is 2, but we'll see that m in this case is not in it's not in a Q. Obviously that's a problem, since we're working with rational numbers. And I mean, if you've taken algebra, you'll know that this is root 2, well, plus or minus root 2, right? But actually, yeah, this is, again, we're defining the real numbers, so we can't use that notation quite yet. And yeah, we'll show that this is not the rational numbers by way of contradiction. So this is our final contradiction. And actually, I encourage you to try this right now. I gave a structure for the proof, and I think it's fairly doable to actually try this on your own. So if you want to do that, then pause the video, but I'll continue on. Okay, so first, let's cut off here. How much space do we have? Oh, we have plenty of space. Okay, so we have this first case, m squared is greater than 2. Okay, so recall that if m is the supremum, then it's the least upper bound. So in order to strive for a contradiction, we want to find m prime such that m prime squared is greater than 2 and m prime is less than m. So if we find such an m prime for any m such that m squared is greater than 2, then, well, there's an m prime less than that m. So there is never any least upper bound. We can go on forever. Okay, well, first, an important thing to note is that this m is going to be somewhere between 0 and 2, right? Because 0 is actually inside of our set, E3, whilst 2 is actually an upper bound. Well, you can check both of these. Because if you plug in 0 into here, x. X is obviously a rational number. 0 is a rational number. So, and 0 is less than 2, so that checks out. And 2, if you plug that in, well, 4 is not less than 2, so that's not in the set. Okay, so this follows, and it will follow for both cases, since there is clearly an element in E3 that is greater than 0. Okay. Well, let's see. Okay, so notice that if m squared is greater than 2, we can write m squared as such. M squared equals 2 plus h, where h is some rational number greater than 0. And we usually we think about it as being very small. We could use epsilon here as well, but I'm not going to because it's not really a place where, I guess, you could, but I just, I don't want to. Usually epsilons are used in like definitions or theorems. This is part of a proof, so yeah. So we have h is greater than 0. What I said there might have been stupid, but whatever. Okay. Let's see. So now let's construct m prime as such. So we have m prime is equal to m minus h over 4. Okay? So we have this, and we know that clearly, since h is greater than 0, m prime is less than m. But we want to show the following here, that m prime squared is greater than 2. So let's square it. Equals m squared minus mh over 2 plus h squared over 16. Okay? But notice that this is actually greater. This is greater than m squared minus mh over 2. Okay? This kind of looks confusing. It looks like I was trying to write a fraction or something. Because, well, this is positive, right? Well, let's see. Now we want to show that m squared, this is actually greater than m squared minus h. And to show that, well, let's just show that minus h over 2 is less than h. Okay? Alright, so, well, to show that, we again create a chain of if and only ifs. This is just going to be, or actually, I guess another more concrete way maybe of doing this is to note that m is less than 2, right? So we have that since h is a positive number, we can multiply both sides by h and then divide by 2, cancel, and we get this. All right, so that's the way of doing it. So now we have established this, but notice that we wrote m squared as 2 plus h. So this is just equal to, well, 2 plus h minus h is 2. And therefore, since we have created a chain of inequalities, we have shown that m prime squared is less than 2. Okay? So that actually finishes this first part, because we found an m prime such that m prime is obviously fits our condition, but it's also less than m. So you can never find an m so that m is a least upper bound for s. Okay, so now let's consider the second case, which is where m squared is less than 2. In other words, well, m is actually in E3. Okay? Well, now it's kind of the opposite of what we want to do right now, right? Essentially, since we supposed that, well, essentially we want to write we want to always find some kind of, how should we word this? Okay, so, in other words, we just want to find, like, I guess this is, I got a bit confused here, but, because we want to think of m as a least upper bound, right? So I had in mind that well, we need to find an m prime such that m prime is greater than m, but I overlooked the fact that, well, since we can just take m prime to be in E3, then m is clearly not a least upper bound, since it doesn't account for all m prime, and it's not greater than all m prime in E3, because there, or all m in, or all x in E3, okay, because there exists something that's in E3 but also greater than m. So that would be a contradiction. So we want to find such an m prime. Okay, well, again, we have so let's actually just take m prime to be, well, m plus h, where h means the same thing as last time, where h is greater than 0, right? And actually, without loss of generality, we can just take h to be less than 1 without loss of generality. You'll see how this is useful. Okay? Well, now we need to fit this condition. We need to make sure m prime is actually in E3. That's very important. So let's take m prime squared. Well, that's going to be m squared plus 2mh plus h squared. Okay. Well, we have the following. Notice that we actually have that m is less than 2, right? Because 2 is an upper bound for the set, and m is actually, in this case, we're supposing that m is in E3, right? So this still holds. Okay. So in other words, and we also have this condition, h is less than 1, and it's not too hard to show that if this is true, if h is between 0 and 1, exclusive, then actually h squared is strictly less than h. And again, using this fact, we have that 2mh is less than 4h. So using all of that, we just have that this is less than m squared plus 4h plus h, which equals m squared plus 5h. So now we want to find h so that this is actually less than 2, right? This is what we want to show here. We want to find an h such that this holds for all m in E3. So solving for h gives us that the condition for h is any h such that 2 minus m squared 2 minus m squared over 5. Okay? Any h less than 2 minus m squared over 5. And note that h still has to be greater than 0. Okay, so now let's just take h to be 2 minus m squared over 5. Okay? Well, for one, we'll show that actually this is greater than, sorry, that's my bad. So for one, we need to show that this is actually in fact less than 2 minus m squared over 5. But also we need to show that it's greater than 0. It's not too hard to show that this is actually greater than 0, okay? It should just be using the fact that m is between 1 and 0 and 2, okay? Whoops. Alright, actually it would be using this because we have like 2 minus m squared. We can we can kind of subtract m squared on both sides, and we can divide by 5, I should say, is greater than 0. So that you can show pretty easily. Anyway. Okay. So now let's take h to be this, okay? Well, first, it's not too hard to see. Yeah, it's actually very easy to show that this is actually less than this, strictly less than this, over, assuming that, this keeps happening, assuming that this is true, but that's what we're assuming, right? So what's left to show is that this is actually greater than 0. So in order to show that, well, there are a few ways of doing this, but I like doing it this way. So I'm going to write this as minus m squared over 6. So I'm going to write this like this. It's an equivalent way of doing it. I probably should just use my cursor. This works much better. But where am I scrolling? But we have this, right? So if we multiply both sides by a negative 1/3, 1/6, right? We have minus m squared over 6 is greater than minus 1/3. But that just tells us that 1/3, adding 1/3 to both sides, minus m squared over 6 is actually greater than 0. So that actually completes this proof. Almost, right? We still have that one last part to finish. Okay. Well, so in other words, I guess to recap what we've done here, well, we found an h. Oh yeah, I guess there's technically one more part here, which is to show that, well, given this h here, this is actually greater than m prime, given this h here, m plus h is actually greater than m prime. And to do that, it's not too hard, right? Because we actually have that 0 is greater than m. Hold on, let me see. And, well, actually, 0 is greater than h. So if we add m to both sides, we have m is less than m plus h. But notice that m plus h is m prime. Okay? Okay. And also we note that m plus h is in our set E3. So again, that actually completes the proof. We found an m prime such that for all m, which we assumed was the supremum in E3, we have something greater than it that's in E3. And that's a contradiction. So finally, the only possibility now is for m to satisfy m squared equals 2, right? And let's show that this is actually an impossibility. In other words, we want to show that m is not a rational number. So by way of contradiction, suppose m is a rational number. In other words, we can write it as, a ratio between two integers. So we have a and b are in the are integers. That's incorrect. Are integers where b is non-zero, and we also have that they're coprime. So the GCD of a and b is 1. This is very important. And I guess to motivate why we can say this is that because if, let's say, the GCD of a and b is like, say it's some c, so like a natural number, right, where c is not 1, well, then that tells us that we can write a as some c times n, by definition GCD, c times m, where the GCD in this case of n and m is 1. Okay, but if we plug that into this ratio here, we can just cancel the c, and then we're going to get a ratio of two coprime integers. We can do this for all pairs of AB. So that's just a bit of motivation. It should be pretty obvious already, though. Okay, well, let's plug that in and square, and then multiply both sides by b squared. And I would be surprised if you actually didn't know this proof. It's a pretty famous one. So from here, one could employ the fundamental theorem of arithmetic, but let's just be a bit, rigorous, other than, instead of just stating a fact here. And we want to show that, so this clearly tells us that a squared is a multiple of 2, right? But we want to show that this implies that a is a multiple of 2. So show that if a squared equals, let's just say 2k, I'm not going to write like k's and, I'm not going to write k's like a natural number or anything. I'm just, so like, I'm not going to write these constants. I'm not going to like define, what set they're in, because it should be fairly obvious. Then let's show that a, just to avoid confusion. So if a is even, a squared is even, a is even. So we don't have to write extra symbols. Okay, well, we're gonna prove this by method of contrapositive. So if a is odd, we want to show that a squared is odd. So we want to show that implies that a squared is odd. So if a is odd, we can write a as some, let's say 2n plus 1. Okay, so a squared is equal to 4n squared plus 4n plus 1. Okay, well, let's see, we can write this as 2 times, well, I'm just going to write it as big N plus 1, where we have that n is 2n squared plus 2n. Okay, we just literally factor out a 2 here, okay? But notice that this is an odd number. So in other words, we've shown this. So, well, that tells us that a is equal to, let's say just 2n. Let's just say, well, okay, let's just say, yeah, 2k, okay? So in other words, we have 4k equals 2b squared. 4k squared, I should say, right? So in other words, we have 2k squared equals b squared. Well, notice that just tells us by the same little lemma here that b is even. But since a and b are both even, that's a contradiction, since by assumption we have that they're coprime. So in other words, this actually completes the proof, because that implies that m surely cannot be a rational number. So I hope you enjoyed the video, and yeah, that was probably a lot to take in, but in reality it wasn't very difficult. It was just a lot of steps to take. Anyway, I hope you enjoyed, and have a nice day. Goodbye.